Кинзбургский? Да. Кинзбургский? Да. Как правильно ударение?
Кинзбургский.
Ага. Okay, guys, so let's get started. And please welcome Stanislav Kinzbursky.
Hello. So today I will talk about live patching and mostly about user space live patching and how it can be implemented with nowadays technologies we have. So let's start with a short summary just to briefly explain what I will be talking about. So a few words about what is live patching and why we can need it, and then some introduction into binary code and process state. Then answer some questions what we can patch, when we can patch, where we can place and how we can play the new code. And few pictures just to illustrate the ideas, and some explanations why I call all this mess painless. And one question to the auditorium, how many of you knows nothing about live patching? Okay, then I will spend some more time on this. Well, live patching, it's very similar to simple patching, like the idea, but you have to patch a running process. So it means that you have to patch binary code by replacing one piece of process logic by another one, and you have to preserve process state when you're doing it, because otherwise you will get segmentation fault or something like this very soon. And you have to replace this piece of code in a safe manner, otherwise it also will fail very fast. And it's, well, quite complicated task, containing of different stages, and there are a lot of questions to solve when you want to do something like this. Well, why it might be needed for someone? It's very similar to nowadays kernel patching technologies. In most of the cases, you don't want to shut down some service. You don't want to interrupt its service work, and but you want to patch it because it has some critical vulnerability or I don't know, some real performance degradation due to an issue in the current running binary. And you want to reduce this downtime, and well, you don't want to restart, you don't want to migrate a program to some other, I don't know, host to replace the software on the original one. Sometimes you don't want to restart a service which takes a lot of time to initialize itself and to, say, boot up. And you also want to save this time. And here are some examples of an existent and used live patching tools. So the most common tools nowadays and quite popular, and it's a hot topic, these tools are known as Kpatch or Kgraft, created by Red Hat and SUSE respectively, and they are used for kernel patching. There is also Ksplice. This is an Oracle tool. They are able also to patch kernel, and they are basically the first tool allowing to do this. And they also, I think, starting from 2015, announces that they can patch user space as well. And actually, there are also there is one more project I found on the internet. It's called Panos. It was aimed to patch user space, but as far as I understand, it actually is not that popular and not that well known nowadays, but it was more like proof of concept, given the idea that we can do this. So when we want to patch a code, we have to understand what we would like to patch. And to understand this, we have to know something about binary code. And binary code is, well, it can be roughly divided into two different types. One of them is called static. And statically linked code, it's the most of the utilities you're using on a daily basis, like ls or pwd or whatever, cat. And by statically linking, it means that the addresses, when the linker creates a binary program, all the references to internal functions or objects like variables is just written as address within a statical binary and as an absolute virtual address. So it in turn means that statically loaded binary has to be placed on the special address specified by linker in the binary file, and on the program start, dynamic linker kernel first, and then dynamic linker do some stuff with the libraries sometimes, and the code has to be placed on some specified location during build time. And there is also a dynamically linked type of binary code. It can be divided roughly into two different types. One of them can be called as load time relocations. This and another one is a position dependent code, and both of them mean allowing kernel to load this piece of binary code anywhere to any address, but these references to data and functions have to be fixed in place during load time. And well, load time relocation is not really widely used nowadays because, for example, you have a function, say you are calling some libc function printf, and you are calling it 100 times, and in case of load time relocation, 100 places. And in case of load time relocation, you have to patch all the 100 calls within the binary code, and it's not really useful and increases load time of the binary. But while position-dependent code works a little bit different, so instead of addressing the function directly from the code, it addresses some other place within this binary which contains the address. So on dynamic load, dynamic linker has to find the address of this function, place it to some cell in memory within this binary, and then all the references to this function will work automatically. So it's faster, but you have an additional jump, like an initial redirection load of an address from this cell. And a few words about process state. So when we know what the binary code is, we have to understand also what the process state is, because we have to preserve it during patching. So the process state is more like, reminds me of card castle. So it's like very tough structure connected to each other. When you're removing only one card, everything else is like falling down. So you have to be very careful with this stuff. And the problem with the process state is that it's changing during runtime, different variables, for example. And it actually contains of three different types of data. It's statically allocated data, some object which you use in your code, like define it in C, for example, like static var. So this address for this variable is placed somewhere in the binary, but you can then, during runtime, the process can change it. Dynamically allocated variables, it's similar, but it's more allocating a variable from a heap. So you just call in malloc, and you get in this dynamical variable and working with it. And also stack content. And by stack content, I mostly also mean here the call stack, because the stack itself is a piece of not the binary, but the process itself, but the call stack, the sequence of functions which was called in the process during runtime is also very important to preserve and to analyze, and I will elaborate a bit on this later. And then we are coming finally to the point of actual patching. So what we can patch. For those of you who know about live patching in kernel, you probably know that it's a very limited functionality, and it also applies to user space as well. So it's a small changes, and these small changes have to fit into the area which doesn't violate some fundamental limitations. And they also can be split into three different types. It's a static data of different size. For example, you have a variable size of 4 bytes int, and then a new binary, new code, works with the same variable, but the size is different, say long. So logic of the code is also changes. Commands, assembly commands, processor commands, they're also changing because the size of the variable has changed. And this can be patched without bringing some disaster to your process. The same applies to dynamic objects. And also you can have some kind of a complex objects like a structure containing of several fields. And if you're adding new fields to this structure, it also breaks this binary compatibility or replacing the fields in the structure, changing the order. It's also not impossible. Okay, possible, but most probably it will lead to crash immediately on the next access to the structure. And all this means that you have to review the source code. So the live patching can't be done in a completely automated way without introducing a huge syntax or lexical analyzer like GCC does, which will parse source code by itself. But you need to see the source code anyway to make sure that the binary patch you want to apply on top doesn't violate these rules. So how to create a binary patch? Okay, you found a new version of a binary, for example, and you know that you can apply it. It's a small piece of code which, for example, checks pointer for null, and you know you can apply it because it doesn't violate any rule which were mentioned before. And how to do this? So a common way of doing it today, like for example, Kpatch or Kgraph does, it's based on function. So the code is replaced by function. You have a null function and you just replace it by a new one. And it's reliable and it's relatively simple. And another approach can be replacing some pieces of logic within the function, but it's quite difficult to get this piece and inject without corrupting the assembly code. And to do so, to get this patch based on functions, you need some information. So you need function name, because you have to get this function address from the binary. And it's usually the function name, the function size, and the function address within the binary is a part of symbols information, which, for example, ELF contains. This ELF is a format for delivering binary programs in Linux world. And you need all this stuff to actually to get the exact piece of code, the exact function to patch the old code. And you also need the old code as well, because you have to find the address of the old code so you can somehow redirect the execution. And the next question is, okay, you created a patch. You made this somehow, you instructed a new function, placed it somewhere in some other file, and you want to apply it to a running process. And when you can do this? Well, it's also not a simple task. So first of all, you have to stop the process, because you can't just simply like changing a wheel on a running car. You have to park it for some time. And what is more important is that you need also to stop it in a proper moment in time, because you have also two limitations applying to this when question. If a process executes the code you want to patch, you can't do it. And if the process, this function is also referenced in the process call stack, you also can't do it, because in this case you can have few threads executing different versions of function. So, which can lead also to disaster very soon, especially if logic changes. So you have to do it safe, and you have to catch all the threads of the process outside of the patching area. So this means that you have to be able to unwind stack, get the full call trace of the process when you stopped it, and analyze it to make sure that you are not going to patch your process when it's running the code. So where we can place this code? Well, with kernel patching, the kernel patching itself, the technology, already has the kernel itself has a load module technique, which really simplifies this problem for kernel developers. So they have to build this patch and make a module around it and load via generic kernel facilities. With the process program, it's not that simple. Moreover, it's quite complicated. So some projects I mentioned before doing user space patching, they have to introduce another system call to the kernel to do this. So either as a module or something like this, and it's not merged into the kernel. So there is no generic way to insert code in a user space process. And even if you found one, sorry?
Isn't there this, are you talking about VM address space, right?
Virtual address space, yes.
Virtual address space, right. This is called.
Sorry.
I thought there's a syscall nowadays to specifically write into the text.
Yes.
Do you talk about that, or is it a new syscall?
No, I'm talking about you have an application, and it's working, and you stopped it. So yes, the question was about what I'm talking when I'm talking about the address space. And so you have an application, it's working in its own virtual address space, and you want to add something, some other code to this virtual address space, and you have to find the place where you can put it. And in general case, you don't have it. So there is a technology, I will also talk a bit about it later, how to write the new code when you have the address space already. But if you don't have, you have to allocate it somehow. And there is no generic way, like a common way to do this nowadays. So you can't, there is for example, system called mmap, which allows you to allocate an address space within your process, but not within alien process. And for example, this project I mentioned in the beginning, Panos, it introduced one more mmap called map3, if I'm not mistaken, which does this mapping creation within a process where we can then place the code. So this is a major problem, by the way, with user space patching nowadays. And it was solved in a way of like kernel modification. But it's not upstream. So it's not like something you may rely on. You have to carry this, for example, the same Panos carries this module with it as a part of a project. Another problem, this is, okay, yeah?
So GDB does something similar, right? It injects
Yes.
call frame for making such an system call from the patch process. So couldn't this be done?
So the question was that GDB inserts the code already into the process, and can this be used? Well, yes, it can. So basically, anyway, it's more about, it's more about not injecting the code itself. It's about creating a space for the code.
I mean, you can rewrite part of the code and then patch it back, right?
Well, you can, but if
There is the current from the system call, then we allocate more memory. Then you got the memory, we can patch back the code that was there already.
yeah, actually, this is actually a solution. So, okay, I can also briefly tell about this later. Right now, and explain what the technologies like more easily used exist today for this. So, since there is an interface in the kernel called ptrace, which you can use to access process internals, and basically you can take a piece of existing address space in the process, and you can inject a small binary blob, which will call for you mmap system call within that process. And you will get the address of a new region allocated within this process, which you can use then to put the code there. Is it somehow? Okay. I will elaborate a bit on this later. So this is quite a significant problem. You can solve it, like I explained already, but it's it's a bit tricky stuff. But you can do this. And another thing which basically applies only to user space patching, doesn't apply to kernel patching, is that you can select one of the two ways of patching user space process. Well, in kernel, you anyway have to load a small piece of code, wrap it as a module, and then use it to patch. Well, in user space, you can, of course, use this way, but you can also do it in a bit different manner, because the code is distributed already, usually. So you of course, can build apply this small change you want to patch to the sources and build the binary and then get it back, like cut out of the binary, and put it as a binary blob, the only small function you want to patch. You also can do it in a different way. You can take a new version of binary where this issue is fixed already and simply map the whole binary into a process and use this new binary. And I will also tell a bit more later how you can even replace the old binary with a new one. Well, so for example, you already know how to place the code into a process, and you decided to put it as a binary blob or just map a new file, for example, shared library. Then you have to, so in case of static code, well, static code is just to, I put this statement here just to make this talk more broad, because patching static code is very painless and actually looks useless. Because the static code, you have to, when you put in a static code into a process address, you can't place it on the same address where the old version was placed, because this address is fixed and occupied by the old code with the whole binary. So you have to place it somewhere, and then you have to fix all the references in this new code to correlate to the variables in the old code, for example, or to some other calls from the function to some other functions. You have to fix all these addresses. And one of the significant problems in this case is that when you build this binary, you don't have the information, and it's relatively difficult to get the information of all these points you need to adjust in case of static code. While the peak code, this position-independent code, which you can place anywhere, for example, like kernel is, or shared libraries like libc, they can replace it at any address in virtual address space, and the code initially compile it and link it in the way that when dynamic linker places, for example, a shared library into process address space, it already knows all the places from the ELF internals wrapped in the binary and giving you information about it. Dynamic linker already knows everything where it has to place the correct addresses. So it has offsets within the library. It knows the address where it places the library, and it simply calculates by summing these things and placing to the addresses specified in the ELF, writing these addresses to the binary code. So it's like more or less simple task, routine. And if you are patching peak code, and I have to say that the rest of my talk will be mostly focused on patching this position-dependent code. You have to initialize variables if you are adding this peak code. So initializing this exactly these places I mentioned, which are not in ELF code, the addresses, which are function addresses or variable addresses in the peak code, you have to fix them. And also you have, you have to copy data in some cases. Because, for example, if this function changes some variable within your binary, within your library, the old one and the new one, they both modify somehow when you are mapping, when you are placing a patch as a binary blob, you can simply redirect it to all data. But if, for example, mapping it as a whole, you can redirect all the references from old library to the new one, simply replacing it, and simply copy data from the old library to the new one. And you need, well, I'm coming to this important point, and well, you need, when you succeeded by placing the patch into the address space and you initialized everything, you need somehow to redirect the execution from the old code to the new one. And here I'm coming to some pictures illustrating how it can be done. So this is how process looks when you started it without any before patching. So you have a process, and there is some function. We don't really care which one. For example, it's a libc function, printf. And your program calls this function several times. And you have these references. So dynamic linker initializes it. It places in your program the address of this function within your address space, so everything is working nice. Then you are inserting code via map system call, either as binary blob, like only function, or mapping the whole library into the address space. And then you're redirecting it like this. This is a common way of doing live patching nowadays. So kpatch, kgraft, whatever else, ksplice, they're doing it like this. So they simply place in jump instruction, assembly jump instruction, which is architectural dependent. They're simply placing this jump instruction in the beginning of the old function, and when you're calling the old function, you are simply jumping to the new code and then returning back. And well, it's a nice way. It's a very simple way because you don't really need much like fixes, and once you initialize the replacement function, you can do this jump and that's it. But there is also one more way which applies to user space, and it has some advantages about which I will call a little bit later, very soon. I call it via replace. So, for example, if you have a libc with some critical vulnerability and you want to fix it, you can mmap or load to the process address space the whole new library. If, of course, it allows you to, if it can be patchable in this way. For example, you have changes only in that function you want. So Red Hat, for example, released a new update for glibc with CVE patch, and that's the only change, and it's applicable in terms of binary patching. You can load the whole the whole library into the address space. You can initialize it in a proper way, copy the data from the old library to the new one, and then instead of placing the jump inside the old code, you can adjust and fix all the references to the old conf functions to the new code. And then you can even unmap the old library. So it's more like swap. It allows you to eliminate this growing memory footprint because you have only one library in process. And it's more similar to the way how code patching looks like when you are using, for example, patch utility in Linux. It simply replaces the old code with a new one. And it's something similar to this. So in user space, it is possible to do such things with position-dependent code like libraries, for example. But you have, of course, in this case, you have to do some work as dynamic linker does. So you have to link the original binary using the libc and all of the other binaries, link it with all this process using libc. You have to find them all and patch all the references to the new library. So, well, why call it painless? Yeah, so it's partially joke, of course, because it can be painless. But what is important here is that you don't need any kernel changes. You don't need any additional system calls. You don't really need prepare this binary somehow. You don't need any instrumentation or whatever else, like in case of the shared libraries, this position-dependent code. And you sometimes don't even need to build it. So if you have an old version of libc or libsSL, and you have a new one, and you had a look into source code, and you know that you can patch it, you can take the binaries which arrived with Yum update, for example, and use them to patch. Well, that's more or less obvious that you you have to get somewhere information. You have to parse ELF structure, which wraps any binary code on Unix distributions. And here are actually some more details in how it can be done. So first of all, these tasks, like task stop, task resume, and code insertion, can be done via libcompel. This is a new library. I appear it as a sub-project of CRIU project, or CRIU, it's online migration of containers, live migration. And it's quite powerful. It hides a lot of this architectural or kernel-specific things like ptrace interfaces and different complex things with registers loading, and gives user relatively simple ways of stopping, resuming process, and also executing system calls. It also allows you to relatively easily load a piece of binary within address space. It allows you to easily execute system call like mmap. You need almost nothing to know about ptrace or whatever else. And the sources can be found as a part of CRU project. And well, it's an alpha stage, but it's working. And well, for stack unwinding, can be used libanwind. It's a mature library, and it can be used to get the stack of a foreign process. So you can, in case of foreign process, alien process, you need to stop it, but libcompel gives you exactly this. So the logic is more or less like, let's stop a process, use libanwind to get the stack contents, check that it's okay for patching, use libcompel to insert the code into the process address space, patch it, and initialize a new code, and then resume the task. Well, so as for presentation, it's actually all. So if you have any questions. Yes, please.
From your experience, do you think that engineers can actually review the changes to decide if it's safe or unsafe to patch the location, or are there too many things around in libraries, long jump, set jump, for example, where you have like out-of-order stores or function pointers that you can't discover? For example, in the kernel, there was a change. Stack 2 was introduced to make sure, for example, that the stack frames are always, even if you go into assembly, that you always have correct control flow information. I think you can't or don't want to change all the build tools to include or verify this information. So how is your opinion on like, is it safe to patch or not patch something?
Okay.
Done by some normal guy, or will it be hard?
Okay. So the question was, how simple is it to patch? How simple is it to make it safe, like in production? And do you need some, I don't know, explicit knowledge to do this or not? Live patching is a very tricky stuff, and it has a limited functionality, and well, it's complicated. So in case of the kernel, you of course have to review the code. In case of user space, it's the same. And of course, if you would like to patch some project, some library, for example, which you don't have enough expertise to review, then, well, it's very risky. So my vision in this case, my hope that since Kapatch succeeded, and it's becoming like a hot topic, it's already a hot topic, and I know that people are also looking, in Zusi, for example, at least, they're looking into live patching experience as well, of user space. I hope that, for example, in case of, say, Red Hat, the guys started to deliver new versions of libraries with fixed CVEs, for example, one by one. Not a bunch of like 10 of them, because 9 of them can be applicable in case of binary patching, and the tense is like changing, I don't know, introducing a new variable, and the whole new package which arrived on your machine can be binary applied. So as for me, I believe that to make it more or less marketable, like that, when you can deliver it to the market to the final user, the maintainers of the source code should try to make these patches for the pieces of code which might be important for live patching, make them safe and small, because they know what they're doing, and they can actually understand that they change the behavior of that the code changes the behavior, like in terms of process state. And well, the interesting thing here is that, for example, if Red Hat starts to deliver, I don't know, updates for libsSL, one update per CVE, then binary patch building, basically, and it can be somehow marked by the maintainers as this can be applied, so this is safe for appliance, and then the binary patch can be generated even on the final host of the client. Because we can, for example, the funniest thing here is that to generate the patch, we need the old binary and the new binary. The new binary is arrived with the package update, but where to get the old binary? And the old binary nowadays you can find in process, in proc actually. So for each process you can find in proc directory called proc-ped map files, and there you can find the old binary, even though it's rewritten by the new version. So you have the sources to create a binary patch on host, and you have a way to apply it on host without any kernel modifications by a simple utility. And that's something on what I hope. Yes, please.
We've been changing the code so that more and more things is compiled with full railroad. What kind of problem does that present for patching?
Could you please repeat?
We've been compiling more and more programs with full railroad, which has the bind now flag. What kind of problem does that present to patching?
As for me, so yeah. So if I'm not mistaken, I will try to say it a little bit differently. So you are compiling the programs with like immediate binding of the external functions, do you?
Yes.
And yeah, and the common way of linking programs is lazy binding, when the function is binded to the process on access. Well, yeah, that's also, thanks for the question. I have to notice that when you are patching like this, like I mentioned, for example, by like replacing the library as a whole, you have to initialize it fully, completely, immediately. So it can be done in a way of lazy binding, because dynamic linker knows nothing about this library, doesn't contain any structures, and an attempt to use it will immediately lead to segmentation fault. So all the internally within this new library, all the addresses have to be initialized immediately. And also all the references to this library have to be initialized immediately before releasing the process. So if I understood you correctly, as for patching, it's just nothing, because we will just do the same.
But we mark the table read-only. So you would have to call mprotect or something like that.
Okay.
Again.
Yeah, so we can write to protected regions anyway.
But I would have a similar case for libraries which are linked with the -e symbolic, where functions calling each other inside the library don't jump through the PLTs, through the procedure linkage table which you are pushing for the allocation case. So if we are just replace a new function there and update the PLT, and you are calling some other function in the library, it still can jump or call the old implementation of the function there.
Agreed. So the question was that when I'm patching only one function, say, or two functions out of the whole library, and this new function somehow references another one which I don't patch, and references it not via PLT, some address table, but directly, in this case, the process can, in some cases, come into the old code, and in some cases using the new one. Well, yes, and that's why I was talking so much about library replacement. Because, well, if you can live patch a piece of code, like if you can live patch only this thing, so it sometimes looks very nice. For example, the new version of libc is released, and it has a lot of changes, so you can't apply it, but you have only one function which fixes some critical vulnerability, and you want to patch only this, and it looks very useful. And yeah, I have to admit it, but it's quite complicated to make sure that you to found all these corner cases like you mentioned, for example. So as for me, since live patch in any way used for small fixes usually, or some maybe small fixes dramatically increase performance, sometimes, and I would like to do it like this way, just simply get the library with a small change and replace it completely. And it also will reduce the memory footprint because, for example, if you have containers, I don't know, yeah, and you are distributing, you have a bunch of them, like tens, hundreds maybe, and they're based all on the same software, and you have this issue everywhere, and a lot of process using this libc. If you are adding only this piece of function, or you are mapping, I don't know, you are leaving the old code with the new one, you're increasing footprint, and it's also not very nice in some cases. In case of kernel, you can't unload the old one, but in case of user space, you can. Yes?
But to replace the whole image, you have to have reproducible builds. What could be a problem?
Well, yeah. To replace the whole image, I need reproducible builds. And might there be a problem or not? Well, I don't really get it in the way of how to say that I do really need reproducible builds. So some things you can when you are creating a binary patch, you have to, and it's actually you have to anyway to parse the ELF structure. And since you're anyway parsing it, you can do some basic checks. For example, function contents. So you changed one function, for example, yeah, and you created a binary, and you created a binary patch out of it, like the old and new one, and you see that during creation, not only this function changed, but quite a lot, for whatever reasons. Then it's a trigger that I don't know. It's like it should tell you that something is wrong maybe, and it's not applicable for patching. So because the live patching itself can be, from my point of view, used either in case you're a developer and you are doing something really understanding what you are doing, or if you want to distribute it across the machines, across the clients, you can anyway, you are distributing packages. And if you are doing this binary difference, binary patch between two well-known, for you, the developer of libc, for example, well-known binaries, you can do it on your side, on the host side, to see that, okay, the binary diff is okay, it's can be applicable against the all-in-one libraries. And since you're distributing exactly the same packages for the clients, like you were testing, well, I assume that you can be sure that the result will be the same on the target machine of the client. Yes, please.
Yeah, maybe a stupid question, like, what if I have the address of the old function stashed in some variable?
Uh-huh.
What's going to happen?
Nothing good. Yeah, I need to repeat the question. So the question is, what if process during its runtime take the address of a variable, global variable, or address of a function, placing it somewhere, its internals, and then using during runtime? And I'm just simply removing this. Well, yeah, nothing good will happen. especially if you are like dropping the old code and placing the new one. Maybe in some cases it can be, you can overcome it by it's a tricky task from my point of view, by trying to place the new functions, the new library to the same addresses, but in most of the cases it won't really work. So.
Yeah, but when I replace just one function and I have a jump in the beginning, it still works.
Yes, in this case, yes, it works. So it's also, it's a trade back. So you have to, with jump it's simpler, yeah. It's really simpler, it's more reliable, but you are accumulating state. So for example, if you're doing this live patching like in iterations for some time, you are getting state. This iteration you patched one function, in another one you patched the same function, in the third one you're patching some more, and you're getting all this state, and you have to take it into account each time when you are patching for the new library. While when you are replacing these things, it's actually stateless. It's simpler to to write this piece of software which does the patching. But yes, you have to review the source code more like deeper, and that's why I was talking also about maintainers. It would be very nice if maintainers could, if the live patching user space will become more popular, that the maintainers will also somehow place a tags or maybe something like this. Yes, please.
Try to use ABI to verify the compatibility of the libraries?
Well, no, not really. Sorry, great. The question was, have I tried to use ABI dev features to check the compatibility of the libraries? So no, I haven't. Yes, please.
So 2 questions. The first one is, what's your recipe for libraries that have non-trivial constructors? Like they execute something non-trivial. What's your recipe in this case? And
okay. Let me answer one by one. So what's my recipe for the libraries which have like a complex initialization routine, yeah? So like constructors. Well, yeah, as well, yes. Well, I don't have any, frankly speaking. So it's, when I was talking about the libraries, I was talking about some generic stuff like global variables, which are initialized in the source code, and these PLT entries and other pointers, but not about something very like special, doing some different stuff based on environment, for example. Yes, so.
And the second question is, do you have any ideas for processes that have more than one stack?
Yeah. Do I have any ideas how to patch the processes with several stacks? Yeah, so-called coroutines, I think. Yeah.
For example. For example,
yeah. Well, yeah, it's a pain, and I think it somehow depends on the way how this stack switching is implemented. So, for example, in Linux we have this set context, make context stuff. And in these cases, maybe it's possible in a nested coroutine which returns to some stack on exit, it's possible to get the structure and check whether it has a pointer to the another one. Because actually this library libcompile I mentioned, it allows you to inject the binary code as well. So it's quite powerful stuff. You can do it more or less easily. So in this particular case, it is possible. But I think it also depends on the way how it's done, and well, I don't really try. I haven't tried to to investigate this question. Yes, please.
It's more a comment than a question, but I don't know if you're familiar with the Erlang programming language.
Sorry, which one?
Erlang.
Erlang, yeah.
And basically, this system was designed initially so that you could do live patching. So I'd say that if you really plan on patching live for several years, your system, etc. You should probably go for a system that was designed for that initially.
Okay.
Try to patch, as you go, with so many special cases and so on. But now, if you want to go with C, what would you say is missing in C that made it possible in Erlang and makes it difficult in C?
Well, so the question was, if I wanna to live patch and I have so many limitations, maybe I should prefer to write applications in Erlang, which was designed initially to do this easy. And if not, well, and I'm talking about C, what is missing in C to support this stuff? Well, I would say that I don't know what's missing in C because it's simply like just language, but it would be very nice from my point of view, for example, if GCC could maybe give some hints during compilation about symbols, some additional stuff, say, I don't know, does it, like, is it call some, I don't know, change in stack, for example, because it's a stack pointer, yeah, because GCC knows it actually, or I don't know, some other stuff. I just really can't specify right now, but maybe a compiler could help a bit to define actually whether we can patch or not, because it's one of the major problems.
For instance, the case you were talking about earlier, where you keep a pointer to the function, things like that.
Yeah, things like that, yeah.
I know that this specific case was thought about on the Untitled API, where all the information has to be fetched, even for indirect pointers. You have to fetch it from the group. So that means that you just have to patch one address, and even if you keep the function pointer, you know that you're going to change the right stuff. But now that was for a very specific API, very specific process, etc. There were a lot of those reasons to do that. So maybe it would be interesting to have a sort of special dynamic patching mode for GCC, where you generate your index.
Yeah, it might be, because yeah, that's actually true. When you load an address of a function on a register, when you're looking into the binary code, you really don't know if it's a function address or it's just a variable matching just the same. When you're doing an absolute load, just placing an address. And if GCC, and of course GCC during compilation, it knows exactly is it a function address or something else, and such kind of information would be really useful for this automated way of checking whether we can patch the application or not. Oh, yeah, last question.
Do you really think that it's a good idea to introduce an extra level of problems? For example, I have a service running. I want to just a tiny patch. It has been reviewed and everything. So I'm going to use this tool to patch it. It's kind of dangerous. So I have to keep up with the tool itself. So I don't know that it's up to date, that it doesn't have any bugs. So do you see what I'm getting at? That there's an extra level of problems which can come up.
Yeah, of course. But it's a kind of a trade-off. If, for example, you have a service and you know, it's just reveal it, that it has a critical vulnerability effect, an issue, and you need to do something with it, yeah? So today, you have to shut down it and restart. Well, yeah, it should be safe to do this, so when you shut down it gently, it has to store all the content, whatever. But sometimes you just, I don't know, you don't have time enough for this, or this application restarts, you know, and reinitializes itself, I don't know, for half an hour maybe. And you have this whole time, the service is shut it down. So it may be worth trying to patch this small change in this case.
I don't know, I'm just imagining it for example, a bunch of containers and just down, you know, the old version, replacing them, and then just patching the other half.
Yeah.
Becomes some kind of
You can do it for sure. It's a kind of, I don't know, rolling update, whatever. You can do it. And yeah, it's a safer way. It will require some more resources from your side. If you have 10 containers running and you need them always running, then you have to start, I don't know, 5 more or whatever aside with a new version and then replace them. So it's more overhead for your host. And it takes more time also for you. But
okay, so it's always a trade-off.
From my point of view, yes. But it's the same like with kernel, yeah? You don't need to patch it. You can simply migrate a virtual machine or container to another node. Can you? Yes, you can. But it's like additional load on network, disk, CPU, whatever. Yeah. Thanks a lot. I'm out of time. Thank you.